Right. Become good. Okay. There we go. Get up there. So I think last time we talked about angles. We talked about radians. We talked about, we basically just talked about angles. Can somebody remind me what radians are all about?
Isn't it just like a different way to measure it?
Yeah. What are they based on?
Radius.
Not really.
Radius.
Yeah, they're based on the radius. Right, so they're kind of like, so guys, real quick. Does anyone know exactly how tall they are? How tall are you?
4'11" or 59 inches.
4'11", okay. 59 inches, okay. So I could say, how many brooks tall is this room, correct? I could kind of like make copies of Brooke, even though it's against some convention, but I'll make clones, and then I'll stack Brooke, right? And I'll see how many brooks tall. Maybe this is like 3.5 brooks tall. Are you guys kind of with me? And I understand. You're like, what the hell is this guy talking frickin' about? But does that make sense? The idea of an inch is made up. How many countries in the world use inches? One. There used to be 3, and then the other 2 caught up with the rest of the world. In America, we're special. Sorry.
That's true.
Talk to any scientist, they'll go a little insane that we just won't use metric. It's crazy. But the inch, the mile, the foot, the meter, the centimeter, they're all arbitrary bullshit. We made them up. So there's no reason why Brooke couldn't suddenly become a standard unit of measurement. We could talk about, hey man, how far away is it? 1,028 brooks. Oh, okay. You guys okay. So what does this have to do with this, dear God, Jeff? Just you making up a story? Thanks, Jeff. No, I can measure the distance around a circle using a radius, just like using Brooke. I can use the radius to say 1 radius, 2 radius. So instead of saying radiuses or radii, we just call it radians. So we know that the word radian just means a certain number of radiuses or radii. You guys semi with me? Okay, so instead of using inches around the circle, whatever, we just use the radius of the circle because that's a nice, the circle gives me that measurement, so I just use it. Oh shoot, let me erase this stuff before I forget. Oh yeah, I gotta talk about that. So a radian is just a physical, natural tick mark that we could use to measure the way around the circle instead of using degrees, which are completely made up. Okay, I love it. Okay, so that's what radians are. We talked about how to convert between radians and degrees, right? Just like 1 foot is 12 inches, what's the conversion we use for radians to degrees? What do we know is true?
180 over pi?
Yeah, 180 degrees is the same thing as pi radians. I love it. Okay. So, before I finish up the first section, so I got to talk about a couple things. There's arc length, there's area, there's angular speed, and so forth. I have a little worksheet for you guys to practice what we did yesterday, but I want to kind of catch everybody back up to what we did. So it was the idea of radians, and then we did angles, coterminal angles, all that kind of stuff. What's a coterminal angle? What the hell does that mean? Coterminal angle. What is that all about? So if I said an angle of 10 degrees, can somebody give me a coterminal angle with that? 370. Sorry, 370. I know it came from over here. 370. I want to give the proper credit. 370, right? What does that mean? 10 degrees, if I go another rotation around, I still end up in the same place. The name coterminal makes nothing but sense. They co-terminate. They both end up in the same place. Let me ask you this. 10 degrees. Can somebody give me a negative coterminal angle? negative 350. So either I go forward 360 degrees. If I go forward 360, don't I end up in the same place? If I go backwards 360, don't I end up in the same place? If I go backwards 360, 360, 720, don't I end up in the same place? So how many coterminal angles exist for 10 degrees? Infinite, 11. So it's just how many rotations you got to make, right? Normally, if somebody asks me for 2 coterminal angles, I'll just add 360, subtract 360. There's 2 coterminal angles. Done. Leave me alone, right? Okay. Now, yeah, let me see. What order do I want to do this in? Yeah, okay, I'll do this. I am going to talk about. Oh, yeah, let me see. Is this? No. A little bit from 7.2. I'll give out this worksheet. You'll work on it, and then I'll come back and I'll finish up arc length area of a sector and angular velocity, in case anybody started trying to do 7.1. Okay. So we know that a radian is just the length you would go along the circle. It's a bent radius, basically. So a radian, 1 radian is the angle you go through if you walk 1 radius along the circle. That's all the radius is. And then in the radian, the beautiful thing again is, if I had a smaller circle, it's got a smaller radius, I would go through the exact same angle if I walked a radius around that little circle. And then if I had this gigantic frickin' circle, its radius is huge, I would still end up at the same angle if I walked 1 radius around the big ass circle. I'd still end up at the exact same angle that I've gone through. Does everybody get that? That's why, when I say 30 degrees, you all could draw a 30-degree angle if you really try, right? You all could do it. And it doesn't matter how long you make the sides of it, correct? Radians, if they're going to be another unit for angles, they have to have that same property. It shouldn't matter how long the sides are, this angle should be the same. And this shows you 1 radian is always the same no matter how big the circle it lives in came from. Does that make sense? However big the circle I make, the radius is going to still take me to the same exact angle. Little tiny one, little tiny radius, go around, same place. Okay, maybe. Okay, that leads to, after some work, how to convert between radians and degrees. Oh man, poor little dude. Hey, there you go. So I can use this conversion to go between radians and degrees. Now, really quick, I think some of you guys heard me talk to one of my students who come here for office hours. He came from my trig class. I'm teaching a trig class. This is the first time I've ever taught trig just by itself. We're about to get into our trig section. So one thing I noticed they had trouble with when I talked about this was radians do not need pi. There's nothing special about pi in terms of if it's radians or degrees. It's just a number. Now pi comes from circles. So yes, there's something special about pi when I'm talking about circles. But I need you to understand, if I say, so for example, if I wanted to convert this to radians, what would I do? Yeah, so I want to get rid of degrees, and I want to change it to radians, so pi radians and 180 degrees. Doing this, putting the degrees here so it cancels, tells you where to put these. And again, if you've ever taken any chemistry, and some of you guys currently are, you're very used to what's called unit analysis, which just kind of makes sure you're dividing and multiplying correctly. That's all it does. And then I would just, put all that shit in the calculator, right? Now again, if I reduce this, I get 11 pi over 18. Can somebody throw that in the calculator? You should get about, you gonna try it, Jeff? Sure. You should get something like 1.97. I don't know. Somebody help me out. What is it? What is it? Holy shit, that's not too bad. I got pretty close. 1.919. I need you to understand this. I can use pi for radians. I don't need to. I can either write it in terms of a certain multiple of pi, or I can write it as a decimal. Do you guys understand? My trig class, they were trying to throw pi in anytime they're raising. Like, if it ain't there, it ain't there. So what do I mean by that? So let me ask you this. What units is this currently in? I'm telling you, that's an angle. What units does it have?
None.
Radian.
Say again?
Radian?
Radians. How do you know that?
Because
I didn't say it's degrees. So right now, it can only be degrees or radians. I need you to be ready for the fact that some of them just won't say anything. If it doesn't say anything, it's radians.
Oh.
If it's degrees, it has to put a degree symbol, right? So what my trig students were doing, when I said convert this to degrees, they were putting a pi in. Well, now that's a totally different number, right? It's not 12 anymore. So how do I convert 12 radians to degrees?
Well, you put pi over 180.
Careful. What is it currently in?
It's radians.
Radians. So what goes on the bottom? Radians.
Radians.
What goes on the top?
Degrees.
Degrees, because I want my answer to be degrees. So now, this cancels with that. Radians, pi radians, 180 degrees. Do you guys see how I don't have to know ahead of time where these are going to go? I just put the unit that goes here to cancel with what's there. Does that? And then you know where to put the numbers. You don't have to know ahead of time where to put the numbers. And now here you just multiply, divide that shit out, right? What's that going to be? I don't know, Jeff. 711. I don't know. Has anybody got that? Anyone do that? What is it?
687.
Darn it, I was way off. 687 point stuff. Degrees, okay. Let me stop for a minute. Okay, so the idea of using a radius to work my way around a circle was kind of revolutionary, right? But it's a beautiful idea because a bigger, smaller circle, they kind of give me their own natural unit of measurement, right? And they happen to always be the exact same angle that I go through, no matter how big or how small my circle is. That leads to a conversion between degrees and radians. Okay, I like it. All right. So, pushing forward a little bit, I'm going to do a little bit from 7.2. We're going to do this little worksheet, and then I'm going to come back and finish up a couple things from 7.1. So yesterday, I introduced the idea of sine and cosine. Does anyone remember anything about sine? You can even tell me how to spell it. That's something.
Sine likes what?
Sine likes what? That is not a very technical way to say it, but it's, who cares, right? It's all about making this make sense. That's what I think to myself. Sine likes y. What does that mean? That's going to help us out so much. At the moment, it doesn't mean a lot. But later you're going to see how this is going to help us out a ton. So if I'm, and what about cosine?
Cosine likes x.
Cosine likes x. So if I have a triangle, and I have an angle in the base, remember theta? So if you weren't here yesterday, theta is the Greek letter that we chose to use for angles that we don't know. Just like we use x and y for algebra. So real quick on the side, theta is the most commonly used one for angles. We also could use alpha, beta, You also see like capital letter A, B, right? So those are the kind of variables they have to use for unknown angles. Okay. If you don't like that, it's too bad. Bless you. They picked it for us. We weren't around. Okay. So let's say that, let me ask you this. If this is 7 and this is 24, how would you figure out that side?
7 squared plus
Yeah.
24 squared.
So 7 squared plus 24 squared equals, we'll call it c squared. Somebody help me out.
Oh,
If I remember correctly, it
49.
should come out nice. Yeah, 25. Good. I should have done one that's a little gross, but too bad. I'll start with this one. We'll do another one real quick in a minute. So the sine of theta, so we kind of shortened the names down to just 3 letters, so it sort of looks like log. The sine of the angle, sine likes y, but who remembers the ratio? Remember, every trig function, the most basic idea of any trig function in the universe is it's a ratio of 2 sides of a right triangle. It's all they are. In about 2 weeks, you're going to be like, holy shit, this is not just ratios. We're going to do a lot of shit with this. But it always comes back to this. It always comes back to this, believe it or not. Anyone remember what sine likes y, but what was the ratio that we set up? The y side divided by
The hypotenuse.
hypotenuse. I love it. So let me call this h instead. This is y, and this is x. Real quick, why is this y? Because the angle's in the base, and this would be the y-axis, this would be the x-axis.
Yeah.
So I'll do a funkier example here in a minute. So the y side over the hypotenuse. Cosine likes x, so you can pretty much guess what its ratio is going to be.
24 over 25.
Well, in general,
Oh, x over h.
I like it.
Is
24 over 25, kick ass. All right, let me stop for a minute. I really want you guys to really, again, later, you're going to lose touch with the idea that trig functions are just ratios of sides of right triangles. That's all they are. So if I give you a right triangle and I ask you for these trig functions, you're like, kick ass. I just got to figure out a side I don't know and then make the ratios whoop-de-doo. So on the most basic level, this stuff is a gimme. You have to memorize what sine is, what cosine is. Can somebody tell me, so we obviously have not created every ratio I could make. I've done y to h, I've done x to h. What's one major ratio I haven't done yet?
C to h? No, C is h. Never mind.
I did y to h, x to h. What about y to...
Theta?
Y to X.
Trig functions are ratios of sides of a right triangle. So I haven't done y to x yet, right?
What?
Okay. I really want you guys with me on this. I need you to understand this. This is it. This is all trig is. This is it. What kind of a ratio of 2 sides can I make? Well, I can do the y to the hypotenuse. I can do the x to the hypotenuse. I can do the y side to the x side, right? That feels like all of them, except I can do all the reverse of those, correct? So these are the big 3. And what we call this one is tangent. Good Lord, Jeff. Hold on. That T went really crazy. The tangent is y over x. So in this triangle, what would that be?
7 over 24.
7 over 24. I like it. All right, so again, nothing crazy yet. Now, like I just said, leave some space right here. There's something that turns this over. This is going to be a crazy ass name. This is called the cosecant. So the cosecant is the reciprocal of sine. But again, it's just another ratio of two sides of a right triangle. So I think the worst part about early trig is just the names of the shit, yes? And the fact that, again, the symbol for the function is a word or a collection of letters. Kusk. So again, for this triangle, all you gotta do is flip this over. Woohoo! Can somebody tell me real quick, is it possible for sine to be bigger than 1? What's always gonna be the biggest side in a right triangle?
Hypotenuse.
Hypotenuse. Sine is the y side divided by the hypotenuse. Can it ever be bigger than 1?
No.
Hell no, because that's always going to be smaller than the hypotenuse, because the hypotenuse is the biggest side. So therefore, cosecant has to be
Bigger than
at least 1. Because it's the flip of this guy. It's always going to have the biggest guy on the top, right? So whatever the hell this guy is going to be h over x, the flip of cosine. And of course, we call this one secant, which is just this piece of that word. So this is cosecant, and this is secant. Now, real quick, I want to address this because this doesn't make the most sense. So we got sine, cosine, secant, cosecant. Tangent, more than likely we're going to have,
cotangent.
holy shit. Right now, when you're first learning trig, the things we call co don't make the most sense. Why did I call cosine instead of calling like cosecant? Why don't I call that cosine? Because it goes with sine. Well, there's a reason, we just don't know it yet. We got to learn some more shit. So I'm addressing something that should trouble you. Why do we call some of these co, and they don't really seem to relate to the other dude? We don't know all the relationships yet. Okay. So this would be just the flip of this guy. And of course, cotangent.
24 over 7?
Yeah, 24 over 7. Okay. So those are the 6 trig functions. So sine will be y over h. Cosine will be x over h. Tangent, y over x. Cosecant will be h over y. Secant will be h over x. And cotangent will be x over y. I took time to write all that stuff down, and I got a little handout that's got all that stuff on it. So you'll see. Let me ask you one thing. Can anyone see a relationship between tangent, sine, and cosine? Help me out, let's do this. What's sine theta divided by cosine theta? Let's see what that is. What's sine theta? Y over h. And cosine theta is x over h. Does anyone know what happens with that? Yeah, the over h is canceled. Y over x, and what's y over x?
Tangent.
Tangent. So tangent theta is also sine theta divided by cosine theta. Which kind of makes sense. If these are all ratios of sides, then they must be ratios of each other in some way. Okay, maybe. Same way that cotangent theta, believe it or not, would be secant theta divided by cosecant theta, but that one's not as important. Okay. We know enough now. We're gonna work on this worksheet. I'm gonna finish up section 7.1, and then by that point we might see what time we have left. We'll see. So I want you guys to I'm gonna catch up to you guys a little bit. I'm gonna start with this one. We got this side of this triangle here.
17.
Yeah. Oops. There you go. The other two, I think, come out gross. Okay. So here, this angle's in the base, so this is y and this is x. That's kind of nice. So it's just like my y-axis, my x-axis. So therefore, these are going to be pretty straightforward. What's the sign going to be? 8 over 17. So that means the cosecant is. Holy shit, Jeff. I love it. Cosecant theta is 17 over 8. Cosine. 15 over 17. I love it. So that means secant. 15 is crazy. And then cotangent. The quickest way to do that is just right there. Right, sine over cosine, so 8 over 15. Not cotangent. Tangent. What's the cotangent then? 15 over 8. I love it. Cool. So that kind of problem is very simple. The weirdest part about this is just the symbols we chose to use. They're little words. That kind of sucks. But the idea is very straightforward.
Are you looking for us to put this in a calculator and like?
No.
Okay.
Yeah. Again, the only problem that I want like a decimal answer for would be a word problem. Let's say how far away does Bill live from work? I don't want to square root of 17 over 3 miles, you know. Then you can make it a decimal, yeah. So in this problem, for example, this is a really good example of this. What'd you guys get for this side?
5.8.
No. Square root of? Anybody do this one? What do you guys get? 34. I like it. So therefore, what's sine theta? It's going to come back. It will. There it is. What do we call y again? This is y here, right? Okay, so what's sine theta? Yeah, 3 over square root of 34. Now, does anyone see the issue with that? Yeah.
The radical in the bottom?
Yeah. We don't like radicals in the bottom. They're weird enough already. So whenever you get an answer like this, you must rationalize the denominator. What the hell does that mean, Jeff? Well, I pretty much almost always just multiply by it. Top and bottom. So then what happens? On the top I get this. What happens on the bottom? 34, yeah. Half of 34 times another half of 34 makes a whole 34. Yay, that's what it means to rationalize the denominator, just make the bottom rational. That's all it means. Kick ass. This poor little triangle I'm going to have to do on the next page, but what's cosecant theta then? Cosecant theta is easier to start here. What do I get when I flip this over? Just flip it. What do we get? Flip this. Yeah, square root of 34 over 3. Cosine theta. What's that going to be? Cosine likes
Cosine
x.
likes x.
Cosine goes like x. So what's the cosine of this? What's the
11
x sine?
over root 34.
5 over root 34. I like it. Can you guys see how you can pretty much go straight to here? Because you're going to multiply by this. Okay, I like it. So what's the secant theta then? Start at the beginning again. What's secant theta? Yeah, square root of 34 over 5. I love it. And then tangent is going to be the one that looks a little bit the best. What's tangent? 3 over 5. I love it. So that makes cotangent
5 over 3.
5 over 3. Crazy. don't know how you feel right now, especially if you've never seen this before. Yes?
Could you explain again why it's 3, 34 over 34 again, and 5?
Are you cool with multiplying by the square root of 34?
So what?
To make the bottom not irrational anymore?
Okay.
So real quick, what's the square root of 9? 3. Why can I do the square root of 9? Because 9 has 2 3's in it. What's the square root of 34? No freaking clue. 34 didn't have 2 anythings. So if I give it another 34, now it's got 2 34's in it. So whatever 34 times 34 is, the square root of that is 34. Because it's got 2 34's in it. Right? That's the basic idea. So there will be times when you actually have to rationalize the numerator, but they're very specific things. In general, radicals are bad enough already. We don't want to also have them on the bottom. It's just better to have 3 34ths of rad 34. That's just better. And then I can put like terms together and stuff like that. So we will always rationalize these poor little dudes if we need to, right? Cosecant doesn't need any help from me because the bottom is already rational. It needs a little bit of help because I left out a letter. So then what about this guy? What do you guys get for this side?
Root 88,
Root 88?
yeah.
Okay, so, I don't know if any of you did this, but what can I do with this? There's the other thing they're gonna have to do when you can do it. I can reduce that, right? I can kind of like simplify that. Isn't this have a square root of 4 in it? And what's the square root of 4?
2.
That's crazy. So then that's the right way to write this side? 2 rad 22. Okay, guys. So anytime, so why couldn't I do that with rad 34? Because that's 2 times 17. I can't take the square root of either one of those, so I can't simplify it. This one I can. If you don't do this, it's not the end of the world, but you have to kind of look for this. So what's sine? I've been writing theta. Sine A. What's sine A? And it's in the base, right? Thankfully. So what's the y side?
2.
Yeah, 2 rad 22 over 13. I like it. Cosine. Yeah, 9 over 13. Thank you, cosine. And then tangent.
2 rad 22.
Yeah, good. The y side
Over 9.
divided by 9. Kick ass. Get back! There you are. Let me stop for a minute. Right? I need you to understand. On one level, you really should feel like, okay, all right, let's just make the ratios. That's it. That's all it is. Just making the ratios. We're going to do an insane amount of stuff with this. It's going to be kind of crazy, the amount of stuff we do with this. But the basic definition is very straightforward. What about cosecant?
13 over 2 rad 22.
So then I have to multiply top and bottom by rad 22. And don't worry about the 2 because he's cool. So I'll get 13 rad 22 over 2 times 22. Is that all right? If I multiply top and bottom by rad 22, well, the top just becomes 13 times rad 22. The bottom becomes 2 times 22. That's rationalizing the denominator. Secant A will just be, thank you, secant. Good. And then cotangent will start off as this, and then it will become, multiply by rad 22, and on the bottom I get the 44 again, just like I got before.
Okay, so you're gonna have to what, multiply that cotangent A?
Yeah, if I multiply,
222 times 222,
if I multiply top and bottom by square root of 22,
yeah,
I get 9 rad 22 Square root of 22 times square root of 22 is 22 times 2 is 44.
Right.
Cool. Okay, maybe. Now there are parts of this to dislike, but overall, you gotta love this shit. You all know Pythagorean theorem, yes? So whatever side I don't give you, you can figure it out. And then you just have to make the right ratio. So you just have to memorize what sine, all you really gotta memorize is sine, cosine, and tangent. Because then the other three are just the flips, right?
Yeah.
Okay, maybe. Just remember sine likes y, cosine likes x. Good. Okay. All right, so going back to this first couple. What have you done, Jeff? There it is. This is degrees, so where am I going to put 180?
In the bottom
On
corner.
the bottom. So normally when I do this, I try to maintain the pi just to make it cleaner, so I don't make it decimal. So how do I reduce 24 over 18?
15? 150?
4 over 3.
4 over 3.
Yeah.
I divide both by 6.
I see.
Real quick. What is pi divided by 3 again in degrees? Pi is what in degrees? 180. So 180 divided by 3 is 60. So later we're going to see that whenever I have an over 3, it's related to 60 somehow. How farther past 180 is 240? How far do I go past 180 to get to 240? 60 degrees further, right? So that's going to become huge later. Just want to point it out. So let's look at this guy. This guy will be, so pi over 6 is 180 divided by 6 is 30. Right? In fact, that's how you kind of do this, right? You remember the shortcut here? Replace pi with 180. 180 divided by 6 is 30. 30 times 5 is 150. How far away from 180 is 150? 30 degrees. I love it. So whenever I see an over 6, it's going to be related to 30 degrees somehow. It's going to be that far away from the x-axis. That's going to become important later. What's this? What's the units on this guy?
Radians.
Radians. Good. So what goes on the bottom?
Radians.
Good. So pi radians, and on top goes the 180 degrees.
Yep.
And normally what we do with this for degrees, we just make it into a decimal. We don't want to leave it over pi. That's weird. So what do you guys get when you multiply all this business out?
1980.
1980? Roughly? Huh? Over pi? Okay, that sounds better. So what's that? 630.25? Okay. So I'm not going to suddenly throw significant figures at you guys. I'm going to tell you how many to round to. If I don't, in general, a couple places is fine. Okay. And then this guy, what do I put on the bottom? Good, because it's in degrees. I want to kill the degrees. On the top goes the pi. And then when I can, I try to just reduce this. What goes into both of these? 3. So I get 11 pi over 6. Cool. And again, it's over 6, correct? Should be related to 30 degrees. How far away from the x-axis is 330 degrees? Oh, shit.
11 pi over 6.
No. Yeah, 11 pi over 6, right? How
30
far away
degrees.
from 360 is 330?
30 degrees.
30 degrees, sure. So over 6 is going to be related to 30. Over 3 is going to be related to 60. Right now, you don't fully understand what I'm saying. Just wanted to point it out while I have some examples. And then finally, I kind of really got you ready for this question. Can somebody give me a negative coterminal angle? How do you get that? Yeah, subtract 316. What do you get?
Minus 231.
231. I love it. And then the positive one is nice because then you just add
489.
360. 49. Kick ass. So if you told somebody to rotate by 489 degrees, they could accomplish the same thing by rotating 129 degrees. It's end up pointing the same direction. I like it. Okay. So, any questions on any of this? So I know a lot of this is new. I really hope I've made radians make sense as to why we want them to exist in the first place, and then how the hell they work. Coterminal is pretty easy to see, it's just extra rotations. These, you might not fully understand yet why we even define these. But it's absolutely amazing the amount of stuff we could not do if this did not exist. It's kind of silly. So we've just started scratching the surface. It shouldn't make the most sense yet. It's just definitions so far. Okay. So last thing I want to do today. How much time do I have? What time is it? I can't see that.
It's 9.
9? Oh, cool. Oh, you guys are like, damn it. He's got too much time. We're going back to 7.1 for a moment, because there's 3 things I want to talk about in 7.1. Let me ask you this. So you have a circle, and the radius is 11 feet. And let's say that I walk, you could do it, Jeff, 1.1 radians worth. You can do it, Jeff. Jeff, stop looking at the monitor. There you go. You guys gonna, so I walk on the circle so that I go through an angle of 1.1 radians. What's the radians mean again? What's radians mean? My question is gonna be this. How many feet did I just walk on the circle? How many feet did I just actually
11
go
times 1.1.
I'm giving myself shit in my head for this poor, pathetic picture I've made. So let me draw some circle. Not too bad. 11 feet. Chumbawamba. Walk through 1.1 radians. Okay. It's a little bit better. What does a radian mean again? Sorry? If I went 1 radian, that would be
Just the
how? What does that
angle-
mean?
this is the
I've gone
angle.
1 what? If I go 1 radian, I've gone the equivalent of how far?
Half pi.
1 radius.
A radius. So if I went 1 radian, how many feet would I have walked? How big is the radius?
11.
So if I went 1 radian, I would have walked 11 feet. Does that make sense? That's all a radian is the number of radiuses that I curved and put on the circle. So if I went 1 radian, the answer would have been 11 feet. But I went 1.1 radians, damn it.
So you what, 12.1?
I want to know the exact, yeah, okay. So what do? I want 1.1 radians. So it's sort of like, Brooke, sorry, you're 59 inches. If I had 1 Brooke, that's 59 inches. If I had 1.1 Brooks, I'm sorry for the 0.1. If I had 1.1 Brooks, that would be 59 times 1.1. That's how tall that would be, correct? So here I got 1.1 radiuses, radii. So it's 1.1 times 11. That's how far I would have walked. If I would have walked 2 radians, do you have to do any work? How far would I have walked? If I went 2 radians, how far would I have walked?
22 feet.
All a radian is the number of radii that I fit around the circle. So, all we do to figure out how long this is, and let me tell you the official name of this is called an arc length. This is an arc, and that's the length of the arc, so it's called arc length. That would just be 1.1 times 11, which is 12.1 feet. So in general, if I want to figure out arc length, and we're going to use the letter S for arc length. Of course we're going to use the letter S for arc length because nowhere in the name does the S show up. But real quick, in general, for some reason, we use S to represent positional change. So S is where I am, so it's how much I've changed position. So S we use for like a distance. Why? I don't know. So the arc length, how did we figure it out? We took, what was this again? That's the radius, and we multiply by, what was this?
That's how far.
And what does that
you walk.
measure? What's a radian measure? The angle, correct? Okay. Do you guys understand that this would not work if I had used degrees? The whole reason this works is because I used an angle measurement that's physical. It's a number of radians. That's why it was so easy to you guys pretty much picked up on it pretty quickly. 1.1 of 11s is 1.1 times 11. You just multiply the damn things. Because radians are defined to be the number of radii. If I used degrees, this wouldn't make any damn sense. So, for example, if I have somebody walking around another circle, I just got these people walking around circles. Don't ask me why. Let's say this circle has a radius of, what do you got, Jeff? 2.5 meters. And somebody walks through an angle of, you could do it, Jeff, 130 degrees. I really want you to understand. Can I just multiply 130 times 2.5? It doesn't make any damn sense because degrees don't match up with radii the same way. I can't do that. Therefore, what do I have to do first?
You have
Turn
to
the degrees
convert.
into radians.
Turn the degrees into radians. So in general, let me see if you guys are cool with this. When I have a trig function, the angle inside can be in any damn units I want to. I don't care how I reference this angle. The cosine just cares about the sides of the triangle, correct? When the angle is free, it's out in the wild, is this angle inside of a trig function? No. Anytime the angle is outside, it must be in radians. It has to be a physical measurement. That's what radians does for us. That's why another rant of mine is, I wish degrees didn't exist. So how do I do this? You guys told me I have to take this angle and do what with it?
Turn it into radians.
Good. How do I do that?
Pi.
Yeah. So you get 13 pi over 18, is that cool? So therefore, to figure out the arc length, I'll take the radius times the angle. And then throw all that mess in your calculator. Don't do 13 pi over 18 and get a decimal, because then you'll approximate it and then your answer is going to be off. Just throw all that mess in the calculator, right? Let's see, 1/6, I don't know, 5/12. It's going to be like 5.5? 40. Somebody save me from myself. 5.3, 5.6, okay. I got pretty close. Okay. 5.67, what?
Radian.
Nope,
Meters.
meters. Meters, yeah. So that becomes an actual distance that I walk along the circle. How do you guys feel about that? That formula directly comes from how we define radians. Radians are how many radii. So if I know the radians, I multiply by the radii to see how far I actually walked. It's actually one of the first things we did when I defined radians, is it just said how far would I walk if I went one radius around. Alright. So this is a formula you need to memorize. 0. Whatever works, whatever works. Okay. Now, last thing for today. So you got this. The book proves this in a different way, and I don't like it. So say I've got this circle, and I've got what's called a sector. And I want to know the area of that pie piece, right? I want to know what area that is. I'm going to prove it a different way. You guys can look at the book if you want to for the other way to prove it. I like proving it a different way. I'm going to take this triangle and I'm going to kind of like rotate it and put it by itself because I just want and it's not quite a triangle. I got to be careful. Why is that not quite a triangular piece?
Because it's got an arc.
Yeah, it's got a
on the
curvy side, correct? Okay. Let me just draw this piece by itself. Isn't this R?
Yeah.
Any line I draw from the center out is going to be R, so that's
Yeah.
R. This is theta. Now, real quick, do you all know that there are people that exist right now who think the Earth is flat? You guys know this? If any of you think that, you're in the right place. There's hope. Why do people exist that think the Earth is flat? Because doesn't
They
it look
can't
flat?
see it, yeah.
So, real quick, let me do this. I don't know if I've done this with you guys, and this isn't anything too groundbreaking. Jeff, you don't have grades up here, do you? No. Okay. Really quickly, hold on. Can you do it, Jeff? Maybe. Did a thing, okay. So if I have a circle, you can see the curve, correct? As I zoom in, does it still look curved?
No.
No, of course not. So that's what the hell's happening to people on the Earth. We're so damn close to the circle that it looks like a line. But if I back out, if I go into space, for example, and take pictures, then you can see the curve. And then they say, oh, you're using the wrong kind of camera. Anyway, sorry. I just love that there's flat Earth. It's just so open. So what's that all got to do with what I'm about to do? So what I'm going to do is, if this was a very small slice, this side would effectively be flat. How long is this side? You guys can do it. What's this length? We just did it.
So radian.
No.
Oh,
Radius.
X is equal to radius theta.
Yeah, so this side is r theta, right? This is r theta. So if I treat it like a triangle, what would the area be? What's the formula for a triangle's area? Anybody remember?
2 pi r.
1/2 base height.
No, not a circle's area. Or that would be circumference. Huh?
1/2 base times height.
1/2 base times side. Half base side. No trouble. Okay. So 1/2. What's the base? Pretend like it's flat.
R theta?
R theta. And what's the height?
R?
R. So the area is 1/2 r squared theta, which is the right formula, believe it or not. So if I pretend like this is a triangle, which it would be if I made it really tiny, this would effectively be flat here. If I made it really tiny. I actually get the exact same formula as you do if you go through all the insanity that the book goes through. I love this. Of course I do. What has to be true about the angle?
It can't be a right angle.
No. It can
It
be whatever
can't
it
be
wants to be,
one.
but it has to be in what units?
Radian.
It's got to be in radians. How do you know? Because it's not inside of the trig function. It's out in the wild. Anytime an angle is out, not in a trig function, it's just out, it's got to be radians. Because that's a physical measurement. Couldn't degrees have been different than 360? So couldn't every angle be something different if I use degrees? Do you guys understand what I'm saying?
Yeah.
So if I would have chosen, does that suddenly make the area of a pie suddenly different if I just call it 400 degrees instead of 360? I suddenly made more pizza? Look at me, I'm magic. I made more pizza? No. So when the angle is outside of a trig function, it must be the only one that's physical, and that's radians. Radians don't give a shit. They're always the same because they're always based on the radius of the circle. It doesn't depend on me just to make up a number like 360. Okay, so real quick example, if I had a circle, and I do, and let's just say this is 3 pi over 4, just to jump to the chase, and this radius is 100 inches. What's the area of this piece? 1/2 times 100 squared times
3 pi over 4.
3 pi over 4. Kick ass. Oh my gosh. Let's see. 500, 1250 times 9. 12,300 and something. I don't know.
30,000 pi over 4?
Somebody say it.
15,000 pi
What do you
over 4.
Sorry? Anybody? No? It's the last thing we're doing, guys. The quicker somebody tells me, the quicker you can leave. What do you guys get? I'm okay if I got it wrong. It's fine. I don't know if somebody's holding back. If I gotta cut it in half, I can't remember if I did that. No worries.
11,780.9.
11,780? Yeah, I got pretty close. What's the units? Nope. This is not an angle. Close. Not meters anymore. This is inches,
Inches.
right? But it's an area. Then I square 100, so isn't that
Square inches.
square inches? Yes. That's a quick way to do it. If your area, it's got to be square units. If your length, you got to be units. All right, guys, that's enough. Next time we'll talk about angular velocity stuff, and then we'll keep going in chapter 7. Next time being tomorrow, by the way. Is that agreed? You're my one class that meets like every day.
Quiz tomorrow?
No quiz tomorrow. Did you want one?